Hello everyone, this is another truth table video that I want to talk about a couple things about truth tables and some of the basic information that needs to be mastered prior to doing more advanced truth tables. I know some of them can be confusing and you have all these scenarios and situations. So I like to kind of focus on the ones that you're going to be dealing with the most, because once you master those primary truth tables, you'll be able to master more complex truth tables. Excuse me. So the first thing I want to talk about is negation, because negation is often used when we have a statement, and in order to negate the statement, it's going to change its truth value to it. And truth tables is a way of organizing information to list all possible scenarios. And we're going to title P as a proposition, okay? And what we want to do is we have a proposition, okay, that we're going to call P, and underneath that, okay, we're going to create kind of like a small little table, and then we want to, second column, we're going to negate P. So let P be a proposition, a statement, and then the second column is the negation. It's also read as, if you look at here, okay, this is also read not P. Oops, I'm having difficulty writing today. Okay, so the tilde sign is not P, it's the opposite of P. Okay, so let's say that we have a true proposition, okay, and its negation is going to be false. So a true proposition automatically becomes false when we negate it, okay? And the opposite holds true. If we have a false proposition, whatever that is, the negation will always make it true, okay? So if you have a true proposition, today is Monday, for example, the negation would be today is not Monday. That would make it false. Okay, or we could say today is Wednesday, okay, which is a false statement, and then in order to make it true, we say today is Wednesday. So it's always going to be the opposite, and that affects the truth value. And we also have another situation where we have logical true and logical false operations. So if we have a proposition P, okay, and if we know that proposition is true, then logically true will always mean you'll have a true statement no matter what the proposition is. So if the proposition is originally true, if it's logically true, then it's going to be true, okay? If something is false, then it makes it true, okay, by logic, okay, logical true, okay? So logical true statements will always be true no matter what the original proposition is. It doesn't matter if it's false or true. A logical true will always be true, okay? Does that make sense? So something can be logically true, okay, no matter what the proposition is. And vice versa, if you have the opposite, if you have a statement that's false, okay, logically false, well, logically false statement will always be false no matter what the proposition is, okay? So proposition is true, logically false will make it false, okay? All right. So you could have that situation where you could have something logically false. Will always be logically false, no matter what the proposition is, and you can have something logically true, no matter what the proposition is. Okay. So let me go ahead and write that down. So this is the logically true one. All right. Logical true. That's what it's technically called. Logical, not logically. Logical true. And that's this right here. Okay. That's this column right here. All right. And then this is logically false. Logical false. Excuse me. All right. So those are your two possibilities right there. Okay. The other, now these are the ones that you really have to pay attention to, because these are used to construct more advanced truth tables. And these operations, and or come up all the time. Okay. So what we're going to do is we're going to list one column is your proposition. Okay. One column is your other proposition. We'll call it Q. You can use any variable you want, but P and Q are often used. All right, but as long as one letter is represented by one proposition and the other letter is the other proposition. So we're going to have two columns. Okay, and for the third column is P and Q. It's kind of like that caret sign. Okay, and here's the thing that you want to keep in mind. Okay, so this is and, okay? The and operator symbolically is used by the caret sign, which is upside down V, also known as a logical conjunction. Okay, so this is called a logical conjunction. Think of together, conjunction, together, okay? And in order to have a conjunction, you have to have two statements, two statements, okay? Two propositions, okay? Proposition P, and then the second statement is going to be Q, all right? And basically the key thing to remember is that for a conjunction to work, okay, if you have a true proposition and a true P statement and a true Q statement, then P and Q will always be true. And that is the statement that we want to focus on. It's this right here. Why is that so important? It's because everything else is going to turn out false. All of the other combinations will be false. So all you got to memorize is that for a conjunction or an and statement, P and Q, if P and Q are going to be true, then your P and Q will be true. Your P and Q is kind of like your final statement, your final conclusion. Does that make sense? All right. If you have these two statements, okay, what kind of conclusion do you get? Do you get a true or do you get a false? It's going to be one or the other, right? So if P and Q are true for a conjunction, then P and Q are true. Everything else is false. So you can just say, this is going to be false, this is going to be false, and this is going to be a false. You're probably saying, well, what? What is exactly false? Well, let's look at all the combinations between true and false. One of them is true, true. And if you get that in an and, your third result is true. Okay? So any other combination that you could think of, let's start with T, a true P statement and a false Q statement. Well, your overall result is false because the rest of them are going to be false. The other combination is a false P statement and a true Q statement. Again, your third result is false. Okay? If both statements are false, then your third result is false. So all you got to remember is for a conjunction or an and, P and Q will be true, okay, if P and Q are true. Everything else is false. Okay? So the only combination you got to remember that's going to give you a true result is true P statement and a true Q statement. All the other combinations underneath that will yield in a false result. So that's all you have to remember for that. And remember, when you draw this using a Venn diagram, okay, that means if you draw a Venn diagram, it's an and statement, so that means you're going to be basically shading everything in here. That's what they have in common. Okay, if you had to draw a Venn diagram, this is not necessary, but I'm just showing you what a conjunction represents using Venn diagrams, just so you know. It will look just like that. Okay? But focusing on the truth table is what I really want you to pay attention to, is what I have in red here. That's so important. Okay? And if we do the opposite, then the OR operator, okay? So if you have P and Q, again, it represents propositions, right? And if you have the V, that's going to be OR, right? Okay? And columns. And what you have to remember is that if you have an OR, then one premise, in order for one premise to be true, okay, an OR operator requires only one premise to be true for the result to be true. Okay, so that third column is going to be your result, the conclusion. So this would be like a union, okay? So let's say you have, okay, so if one premise has to be true, okay, if one premise has to be true, then the third result will always be true. It doesn't matter what Q is, okay? So again, we're thinking of all the combinations here, right? So if you have a true proposition, okay, then what's going to happen is if Q happens to be true, then your third result will be true. We got to think of combinations. Another possibility is if you have a true proposition, P, and you have a false second statement, your third result is still going to be true, because all it requires is one of those statements must be true. Does that make sense? Okay. Let's say you had a false, P statement, but again, your true statement is Q. Hey, you still have one true statement. Okay, and this time it's Q. That's okay. It still satisfies the condition of one of those statements being true. Therefore, your third result has to be true. Okay? And that's what you have to remember, is that an OR operator requires one of the statements to be true. Okay? So, the three combinations, true, 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 false, true, false, true, true. You notice the third result here is all true, because one of these propositions, okay, in the first and second column would be true. Does that make sense? Okay, and then of course, if both propositions are false, then the third has to be false, because we didn't start with one true statement. We start off with both false statements, so that doesn't meet the condition that one of the columns is true. Okay, and if you draw this using a Venn diagram, this represents a union, which means all of the elements in both sets. So really, you would just be shading in everything in both circles. All right? Okay? And that's so important. Okay? All right. Okay, so the next thing I want to talk about is going to be conditional statements. Okay, implication, logical implication. Okay, so for this particular truth table, okay, we're going to start with our P and Q, and the third column is your conditional statement, and basically that reads if then. So if P, then Q. Okay, so if P, then Q, and that's called your conditional operator. Okay, so this is conditional. Okay, so and basically what we want to do is we want to make sure that when we do this, okay, we want to keep in mind that if you have something like this as a little bit of a footnote here, okay, so it can be helpful to realize that this conditional operator is logically equivalent to not P or Q. Okay, so what we want to do is we want to have a table. Okay, so if you have a true proposition and a true P statement and a true Q statement, then your third result is going to be true. Okay, and if you have a true P statement and a false Q statement, then your conditional result will be false. So how do you read this? If P is true, okay, and Q is true, then it'll be resulting a true statement if those conditions are met, okay? And if you have a true statement and a false statement, then your overall condition will be false, okay? And the thing to keep in mind is that you can have a false proposition and a true proposition, doesn't matter the order, okay? Well, actually it does matter. In this case, if the first proposition is false and the second one is true, then your third result will be true. Previously, if you have a true P statement and a false Q statement, that's the second one, then your overall condition is false. If both of them are true, then your third condition is always going to be true with a conditional, okay? And if you have a false P statement and a false Q statement, your third statement will be true, okay, according to the conditional operator. So everything is true except for this. This is the only one that you have to remember. If the first statement is true, followed by a false second statement, then your overall condition is false. Everything else is true. All the other combinations will yield in a true statement. So try to remember the one that is false in this case. It'll be easier to remember. Okay? All right. Now, let's go to this situation. Sorry about that. Let's create a second truth table to demonstrate the logical equivalency that I mentioned before. Okay, so remember I said that if you have P and Q, if P then Q, I said it was logically equivalent to, I'm gonna go ahead and just use the symbol logically equivalent so I don't have to write it out. Is logically equivalent to not P or Q. So remember the upside down, the V here is or. All right, so let's say you're given we're going to make our P and Q columns. All right, okay, so let's think of all the 4 possible combinations of true and false when we have 2 statements, right? One combination is true and true, right? 2 true statements. The second combination is one being true, the other being false, right? So the first proposition is true, followed by a false second proposition. And then you can reverse that. You have a false proposition followed by a true proposition. That's your third combination. And then your fourth combination is both statements are false. Those are the only 4 combinations that you can get, right, with true and false. So you will list those. The third column is we're trying to figure out this, right? Actually, we'll leave a space for the third column and let's do a fourth column. Remember we said if P then Q is logically equivalent to not P or Q. Okay. Well, in order to master that fourth column, we need a third column. And you notice that here, actually I'm going to do it in red. You see this is not P. We don't have a column in our truth table that represents not P. So it's in our best interest to do that and create it. Because we want to analyze what the truth values are for that fourth column, not P or Q. So we list all the combinations of P and Q in our first and second column. Let P be the first statement, let Q be the second, and then just list all the combinations. It doesn't matter the order, you can just list them, okay? You can put the false ones first, does not matter as long as they're listed, okay? However you remember them. And then now, look at your first column. Your first column is your P, right? True, true, false, false. The third column is the negation of P. Well, we want to negate every statement in the P column. So originally, my first P statement was true. So if I negate that, then that should be false. My second P statement is also true. So I'm going to negate that. That's false. My third P statement is false. So the negation of that is true. My fourth P statement is false. So my negation for that is also true. And now we list the negations of every statement in the original P column. Okay? So, all right. So, again, my first P statement was true. I made it false. My second P statement is true. I made it false because the negation is always the opposite. Third P statement is false. I negate it. It's true. Fourth P statement is false. I negate it. It's true. Now look what we want to analyze. We want to analyze this. This V is an OR. So we need to OR. When we do the OR, we're not comparing P and Q anymore. We're comparing the negation of P and column Q. Okay? So we're analyzing the negation of P and the Q column. Okay? So remember, if you do the OR, remember what I said, you will have a true statement if one of the statements is true. Okay? So we'll do the first one. The Q statement here, and I'm pointing right here, is true. Okay? And if that second one is false, that's okay. That's still going to give me an overall true statement for this column. Okay? Now look at the second column. I want to OR the Q and the negation of P. Well, they're both false here. So therefore, that is the only combination that'll give me a false result. The third column, hey, one of these, not only one of them is true, but both of them are true. Again, as long as one of the columns is true, we get an overall true result. Okay? So, and then look at the fourth. Okay, look at the Q here is false, but look at this, the negation of P is true. hey, one of those is true, therefore the third result is true. That's what I mean by ORing, right? If you know the OR, the rules of OR, you just pick the two columns you're trying to do the OR, and then all you got to remember is, hey, if one of those statements is true, I'm going to get a true third result. If they're both false, then that's the only time where I'll get a false result. Does that make sense? So let me just recap that, right? In the Q column, one of these statements is true, okay, even though the negation of that is false. Hey, the rule is, if I want to do the OR, then one of those statements has to be true, therefore I'll get a true result here. Okay? In my second column, both are false, so therefore my third result is automatically false. That's the only thing you got to remember. And then my third column, both of these are true. As long as one of those columns is true, my third result is true. And then in my fourth column, again, my negation of P is true. Hey, that's one of them, therefore my third result is true. So that is the trick there to remember for OR. There is one more I want to show you that you're going to see quite often. This is called biconditional, and that's if and only if. Okay, so biconditional is easy to remember, and that's noted as if and only if. Okay, we're still going to use P and Q as our statements, our propositions, because it's so frequently used, so we'll just be consistent. Okay, so our first column should always be our P, second column should always be Q. And to write if and only if, so we can say if P and only, I want to use the symbol, not the word here, sorry. We need the arrow. Whoops. Okay, it's going in both opposite directions, right? So if and only if represents that conditional statement where the arrow is pointing in both directions on both ends, okay? So anytime you see that arrow in both directions, that's a biconditional statement, okay? If it's just going in one direction to the right, then it's a conditional. So think of two arrowheads as biconditional. You know what I mean? One arrowhead is conditional, and then the second arrowhead is biconditional, if that makes any sense. Maybe just think of some kind of mnemonic device way to remember it to help your memory, because I know this can be a lot. And the cool thing about a biconditional statement is the only thing you got to remember is a biconditional statement can only be true, okay, if both original propositions P and Q are true. That'll yield a true biconditional statement. Okay? And if you have two false propositions, then that will yield a true biconditional statement, believe it or not. So those are the only two that you have to remember. The other combinations would be if you have one of them being true. Let's say you had a first true condition and the second condition is false, then that's going to yield a false biconditional statement or result. And vice versa, if the first condition is false and the second is true, you're still going to get a false third result. Okay, so that is, the only way we can assert a conditional that holds in both directions, as if both P and Q have the same truth value, then they both will have the same truth value at the end. So if both conditions are true, your third result is true. If both original conditions are false, your third result is still true. That is logically equivalent, okay? Or logical equality, as they call it, actually. And that's the basic of truth tables. Once you master these tables that I've shown you, then you can or and any other truth table. Okay, so again, I know it can be a little tricky and overwhelming with all the symbolism and combinations, but I think it's best to really master what and or are, okay, and know the difference of the third result, okay, when you have an and or an or situation. And then once you do that, okay, when you're given more advanced truth tables and they ask you to or two columns, whether one is negated or one is not, you just got to memorize the rule for or, and vice versa for and. You have to master that first before you can do other truth tables, because if you struggle with those two, then you're not going to be able to do and this is just in my opinion, you're going to struggle with more advanced truth tables. They're going to be it's going to be more like guessing. You're not going to know what to do. So it's better if you master the and the or concept first before you move on to conditional and biconditional and more advanced truth tables. All right. I hope this video finds you well, and I hope that it has been helpful. Thank you so much for watching, and I'll see you in the next video.